the what? Okay, so welcome to the webinar organized by the Image Analysis and Data Fusion Technical Committee of IEEE Geoscience and Remote Sensing Society. So this webinar is part of a webinar series organized by the 7 technical committees of IEEE GLSS. I am Nautioka, the chair of Image Analysis and Data Fusion Technical Committee, which aims to connect people and promote activities related to image analysis and data fusion in the remote sensing community. From this year, to expand our activities, we started to organize 3 working groups. And the first one is machine learning for image analysis. The second one is image and signal processing. And the third one is benchmarking. And the leader of the first working group, which is machine learning for image analysis, is Professor Claudio Persello. So he is today's speaker. So he's one of the leading scientists in our community who really deals with social problems using remote sensing and state-of-the-art deep learning techniques. So today he will talk about mapping urban deprivation and socio-economic inequalities using Earth observation and deep learning. So the stage is yours. Claudio,
thank you very much, Nato. Yeah, thanks for the nice introduction, and welcome everybody to this webinar. Thanks for joining us. The topic of today is the result of a variety of research activity carried out in at the University of Twente, in particular at the faculty ITC, and is the result of the collaboration with several colleagues, students, and PhD students. So we'll give you, let's say, an overview of a few research lines which are related to mapping urban deprivation and socioeconomic inequalities using Earth observation and deep learning. So let me start with a short introduction. The rapid urbanization and population growth, which is taking place all over the world, but especially in low and middle income countries, lead often to the proliferation of deprived neighborhood, also called slums or informal settlements. According to recent statistics of the UN Habitat, there are currently 1 billion people living in informal settlements, living in unhealthy conditions and lacking essential services such as clean and safe water, acceptable sanitization, and durable housing. In addition to that, the communities living in these areas are among the most vulnerable to climate change and the increased risk of natural disasters, such as droughts, storms, heat waves, floods, and so on. Unfortunately, these areas are invisible, often invisible in official maps and statistics. And this prevents to put in place proper policy and measures to try to address the problems. So in this context, Earth observation allows us to map and to monitor these areas. And this can give us a more realistic view of the urbanization processes that are taking place. And this often reveals the large socio-economic inequalities. Urban poverty and informality is also a global phenomenon, is a global societal challenge, which is also recognized by the UN Agenda for Sustainable Development. And in particular, the SDG 11, which is aiming at making cities inclusive, safe, resilient, and sustainable. Target 11.1 is looking specifically at slums, requires or asks countries to ensure access for all to adequate, safe, and affordable housing and basic services. So also in this context, remote sensing, both based on satellite images or also other platforms such as aerial images or UAV images, allow us to provide useful geospatial information to support the achievement and the monitoring of this sustainable development goals. One particular indicator which Earth observation allows us to monitor is indicator 11.1.1, which aims at estimating the proportion of urban population living in slums. So in the next slides, I would like to show you some of the research activities done in this direction using different platforms. And I would like to start by showing some of the activity done towards investigating the use of unmanned aerial vehicles or drones to map informal settlements. The good side of this platform is that UAVs allows to acquire very detailed information, very high resolution images down to a few centimeters. And thanks to photogrammetric and dense matching techniques, we can also extract three-dimensional information from these images in the form of point clouds or digital elevation models. This rich geometric information is very important for mapping applications and also is suitable for supporting upgrading projects that aim at improving the livelihood of people living in slums. And one of such projects was based in the city of Kigali in Rwanda, and our activity was actually linked to that project. And you here in this slide see two images, one image and one point cloud acquired in the city of Kigali. What we have done, we have investigated different classification schemes, which are able to take advantage of the characteristics of UAV data, which provides information in the form of two-dimensional images, but also, as I said before, in the form of a digital surface model and three-dimensional point clouds. And our investigation also looked at way to properly combine these different data sources to improve the classification performance. And before moving to deep learning, we have investigated solutions based on support vector machine and multiple kernel learning to exploit the specific statistical properties of the different data sources. We have also looked at monitoring changes and the evolution in time of informal settlements. And as you can see in these figures here, here are images again acquired in the city of Kigali in 2015 and in 2017. And through the upgrading project, new activity have been planned, like the building of a new road that you can see is visible in the most recent acquisition. And also some other buildings have changed and you can see some other changes on the ground. So we have investigated and developed a change detection method to produce automatically maps of the changes. And what we have done, we actually have combined the power of deep learning and its ability to automatically learn spatial contextual features from the data itself with expert knowledge. And we adopted a rule-based approach for automatically extracting training labels. So basically, this combination allows to train deep learning network without manually labeling the data for training the network. and also allows to produce maps of changes that distinguish different types of changes. So these are semantic changes. And here you can see the maps on the right side, where we have changes where new buildings have been built, but also the opposite case is possible, where buildings have disappeared in the new acquisition, or simply the roof material has been changed or improved thanks to the upgrading project. So this approach allows us to completely automatically map the changes over an informal settlement. Moving now to the space, so to say, we have also investigated techniques to map informal settlements using very high resolution satellite images. And in this case, the idea is to detect and to map the distribution of the slums over, for instance, large urban areas. The challenge in this case is to extract the features, the spatial contextual features that allow us to discriminate different urban areas. And also one challenge is simply associated to the difficulty to define what actually constitutes a slum and what is a formal settlement. So standard methods looked at techniques based on object-based image analysis or grayscale or gray level concurrence metrics, which allows to characterize the texture of the image. Indeed, if you can see in the image here on the right side, which is an image acquired over the city of Dar es Salaam in Tanzania, you can see the informal settlement. Now we'll highlight where it is located. Well, it's characterized by an irregular layout of the urban structure and almost no presence of green areas. But all these are spatial contextual properties that are not related to the spectral signature of the signal. So really, it's important to extract and possibly learn these spatial contextual features. And here is where, let's say, deep learning can provide a major advantage with respect to traditional machine learning techniques. And for this reason, we have investigated convolutional networks, or more specifically, fully convolutional networks to produce semantic segmentations of the image, therefore detecting where the slums are distributed over a city or a region. So what we have done, we have investigated a fully convolutional network employing dilated kernel. The idea of this architecture is to be able to capture large receptive field, because indeed, if we want to classify and recognize slums, we need to capture this long distance pixel relationship. And one way to do that would be an alternative to use an encoder-decoder type of convolutional networks, like it is done in famous networks like UNet or SegNet. In this work, we decided to go for an alternative solution where the network doesn't employ any downsampling, and then later on also no upsampling. But all layers keep the same spatial dimensionality of the features. And we use increasing dilated convolutions to capture the large spatial dependencies. So in a way, this is resulting in a quite simple network design, which allows to easily add or remove layers according to the specific characteristics of the problems or the data. And yeah, nowadays also dilated kernel are used in more recent developments like DeepLab and so on. Here are some of the results that we obtained by applying our fully convolutional network to mapping slums in Dar es Salaam. Here you see the two tiles that we have used for the experimental analysis, and the map produced by different classification techniques. So clearly what FCN shows is a higher accuracy with respect to traditional techniques, but also a much more computationally efficient approach with respect to patch-based convolutional networks. So resulting in much faster mapping at testing phase. Another aspect that we have looked at is to analyze also the temporal dynamic of informal settlements. In some of the cities, the city evolves quite rapidly. And in this case, we did a study in the city of Bangalore in India, where it's quite common to have temporary slums. So these are temporary slums characterized, as you can see in this image, by tents, these blue tents. And they really change very quickly in time. And here you can see some images taken at different times where the slum is gradually disappearing through time. So people are actually moving towards other parts of the city quite quickly. And what we have done, we have developed a change detection algorithm designed to actually analyze this temporal pattern in the slums. We have investigated two general approaches to architectures. The first one is a post-classification change detection. It's basically applying a fully convolutional network to both images and independently, and producing a classification map. And after that, the two classification maps are compared to obtain a post-classification change detection result. Another approach, alternative to this, is to simply combine the bands, the features of the two images, and then train the FCN to directly predict the changes. We have seen, let's say, pros and cons of these two different strategies. In general, we obtain higher performance with the first approach. And also one additional advantage is that in this case, we can also map the different type of changes. So we can also semantically characterize the changes. In the second case, that is a little bit more difficult and is possible, but is a little bit more difficult because the types of changes have to be modeled as specific classes. So we need to have training samples of all possible class transitions. But an advantage of the second approach that tends to produce more regular, spatially regularized maps, often avoiding irrelevant changes, which are simply due to some small misalignments between the images. Another topic, I think a very fascinating one, is based on the fact that we wanted to go beyond what we have seen so far. All the methods I've described so far for mapping slums basically model the problem as a binary classification one, where we simply classify pixels as slum or not slum. But this assumes that there is actually a sharp decision boundary that allows us to distinguish what is actually slum and what is not. But often the definition is very difficult to give a definition, and it varies from country to country. And another problem is that slums are very different and can be associated to different forms of deprivation or poverty, which are not necessarily associated only to the physical level, so how the slum appears in the image, so the layout of the urban area and so on. But there are also other characteristics that somehow pertain to the study of poverty, which are beyond the physical domain and includes the financial, the human, and the social domain, which can be only observed indirectly using images as a proxy. But what we wanted to do is to, let's say, go beyond the binary maps to be able to map and estimate a socio-economic index of poverty. So what we have done in the context of this study, we designed a deep learning method to map, to estimate the socio-economic conditions in the city of Bangalore. And the idea is then to predict, to model the problem as a regression, to predict a continuous valued index of multiple deprivation. And we, first of all, let's say the method can be presented in three steps. First problem that we had to address is how can we characterize the deprivation, and we have done by developing a data-driven index of multiple deprivation that takes into account all these different forms of deprivation and combines a large set of variables into one single index. After that, the second step is to train a CNN to predict this socioeconomic index. But there is actually, well, quite a challenge in this context. And the big problem is that to train convolutional neural networks, you usually need a large training set, which was not available in our study area. So we will see how we adopted a transfer learning model to try to tackle this problem. And finally, the third step that we applied is the extrapolation of the model to predict the socioeconomic variability over the entire urban area of Bangalore. So I will just quickly show you the data set that we have used in the study. So we had access to quite, let's say, rich data set collected on the ground. And these are socioeconomic data. And we have two specific data sets. One is what I call this HH, household survey-based data set, where basically the household people have been interviewed and several information about the household have been collected. This is a very, of course, time-consuming process that allowed us to collect this detailed information only for 37 slums scattered in the large urban areas that you can see here. These are the red dots in this map on the bottom right corner. But we had also access to what we call a quick scan, which contains a set of variables that can be collected simply by walking through the slum, by a person noting down a set of characteristics. So without interviewing the people living there. And this less detailed information are easier to acquire. And we collected a larger sample. And in this case, 121 slums have been surveyed. And these are the blue dots in the map. Of course, we had also access to images, in our case, Pleiad images. And the combination of 4 of them allowed us to cover the entire city. And an additional information that we will see is very useful. We also had delineated slum boundaries for more than 1,400 slums in the large city. So how did we take advantage of that? So as I said before, it's very difficult or almost impossible to train a CNN to predict the socioeconomic index on the basis of just 121 samples. So what we did is we first pre-trained the CNN model on the problem of classifying patches as either being slums or not, using the larger set of samples, the delineated slum boundaries. So with about 2,000 samples, we could actually train properly a convolutional neural network to classify and distinguish formal and informal settlements. And then we use actually the features learned by the model as good variables for predicting then the socioeconomic index. So these features are actually, and we will see later on, a good proxy for then predicting the socioeconomic variability. And we use two different convolutional networks based on the popular VGG network. Oops. So these are some of the results of the analysis. We conducted a 10-fold cross-validation. And what you see on this table here are the results of the coefficient of determination, R-squared, for different regression models using different sets of features. And the best of our models, which is taking advantage of the CNN-based or CNN-learned features, is able to explain the variability in the socioeconomic index with an R-square of 0.75, which is in a way quite a good result. We were quite happy with this, to see that basically by using CNN we can extract these features that allow us to really somehow capture the different forms of deprivation and estimate this socioeconomic index. What you see on the bottom right side is then the map that we extrapolated for the entire urban area, for the entire city of Bangalore. A few details here just to show you visually how what it means to predict this different socioeconomic index. You see here a set of pictures collected on the ground for some of the worst of slums. And as you can see, these are these typical temporary slums, which are, of course, well, lacking access to essential services. And you see also this on the bottom left corner of these pictures, the corresponding satellite image, which is used by the CNN model. And you can see also for each of those pictures, the observed value, which is extracted using the household data. And you can also see the predicted value obtained by the CNN-based model. So, of course, there are some differences, but actually it shows that there is a general agreement of the predictions of our CNN-based model. And what you see here, all this index takes negative values for the worst of slums. And on the contrary, the best of slums take positive values of this socioeconomic index. And here you see again some pictures taken on the ground of some of these slums. And maybe some of the slums went through a gentrification process. And even if they are still considered slums, the people there have developed better living conditions and the better infrastructure. That's why they have also associated to a better socioeconomic index. Okay, with this I would like to try to draw some final thoughts based on the different research activity carried out here in ITC. On the positive note, well, we actually observed that the combination of Earth observation and deep learning can result in very useful tools for mapping slums, for producing maps giving a spatial distribution of where they are in a large city, and possibly going beyond that to regional or country level. They can be used also to go beyond the binary classification and can be used to estimate socioeconomic variability. One, let's say, advantage of using an Earth observation-based approach is that this can produce relatively consistent maps across different countries, whereas standard statistical methods would use different approaches in different countries, which is probably one of the, it's one of the big problems when assessing or monitoring the target indicator of the Sustainable Development Goals, because different results of different countries are not directly comparable. But of course, there are also many open challenges, many things that still need to be addressed. First of all, I would like to mention, well, what I've presented are several research activities carried out in different cities, different parts of the world. But of course, it would take major efforts to translate or transform these research results into operational solutions put in place by governments and organizations that can take advantage of this information for decision making and for planning interventions and so on. On the more technical side, I think there are several issues. One, of course, is related to produce maps which are consistent across different cities or countries. And this refers to the problem of transferability of deep learning models. Another very relevant problem is to make deep learning models trustworthy, to make people rely on the results of deep learning models so that they can use this information for decision making. And this is often still not the case. So I think this is a challenge for our community to work in developing models that can be trusted by authorities and then act based on the information provided by those models. Other open issues are related to estimating population density. It's still a big problem. Also because current statistics based on census data are often not comparable or often inaccurate, or there are many inconsistencies in the currently available data. And probably in many cases, the slum population is largely underestimated, but we have no actual way to show or to evidence to say that. But this is, of course, something to investigate more on. And other aspects, of course, are related to assessing the vulnerability of informal settlements, and especially related to risk of floods or heat waves. So many of the slums are in these risky areas of the cities, and therefore they are particularly vulnerable to these risks, to risk in general of natural disasters. Okay, thank you very much for attending this presentation, and I would be very happy if you have any question for me. Would be very happy to answer your questions. Maybe one thing I forgot to say, you could to write questions if you like in the chat box, and then I think with the help of Ronnie, we can try to go through the questions, and I would try to reply to your questions or comments.